And before we dive into the technical material, I just want to say, feel free to type in your questions into the chat of Zoom chat or onto Slack. Zoom chat will be the easiest, most direct way, so we can just answer them there. So I have all my presenters here, so I think we'll just go ahead and start. Welcome everyone. This is the tutorial on the advanced exploits for system security assurance. I'm Daphne Yao. I'm a professor at Virginia Tech. My co-presenters are Salman, Ahmed, who is a fifth-year PhD student in my group, Professor Cheng, who is assistant professor at Clemson University, and Hans Liljestrand, who was a postdoc fellow at University of Waterloo and now recently joined Intel at Finland, and Professor Asokan from University of Waterloo. And this is we have collaborated, the team has collaborated prior collaborations, and we all I feel that this is a very important topic that we'd like to talk about and just understand what system security, the most advanced type of system exploits are and what are the defenses. Salman will be leading a demo. Hans will also give a demo. Here are some information, and Salman will enter some of the links into the chat window. So for some of you, if you'd like to follow along, you can start to download the code and play along. Later we'll have a relatively quick demo. The purpose of this tutorial, there are two levels. The first is to understand the advanced attacks and the defenses. But then really our ultimate goal is hopefully to inspire people to generate better defenses. It's really, you have to understand the attacks in order to find ways to stay ahead of attackers. And hopefully it's not incremental. Hopefully you will prevent future attacks and the better kinds of attacks and more types and categories of attacks. And one of the methodology that we'd like to cover is the measurement, the system measurement in the cybersecurity domain. In security, we all know is relative. And this not just secure or not secure, it's always under certain conditions with respect to certain attack conditions. And then you really have to have a very fine-grained way of measuring the security guarantees and understanding all the delicacies and all the subtleties in the conditions. And so we'll show some examples of how security measurement can be done and hopefully inspire other work in this domain. And we'll cover a lot of topics ranging from code reuse attacks, address space randomization, coarse-grained, fine-grained, data-oriented attacks, which are newer kind of attacks, because a lot of the control flow integrity solutions prevents control flow attacks. And so data-oriented attacks circumvent that. We also talk about hardware-assisted protections. But this is all under the general topics of system security, advanced exploits. Some of the work results is based on the CCS work where we measure the many aspects of ASLR, even though people have thought that it's already completely solved, but then it turns out there's a lot of conditions. So how to achieve the best randomization? Do new attacks like just-in-time return-oriented programs still be launched under fine-grained ASLR? And so another work that is covered is our journal paper at ACM TOPS, which is on data-oriented attacks, understanding how it works, different flavors of it, how is it different from control flow attacks, and what are the possible defenses. And this is a relatively new attacks, and we're still getting to learn more about it. And so we're going to share some of our understanding and hopefully inspire the work. And then the reason that we want to do this is because in security, especially system security, everyone wants to come up with new solutions. And then you end up have a whole bunch of new solutions, and then you lack of a general big picture of how everything is connected. And really our field of system security really needs a lot of work to systematize all these different components and figuring out a map. And so we hope to make a small step in this way. And if you see attacks, and usually it's not just one step. You attack. it's multiple components, multiple phases. In here we listed the 4 big phases, and it's all under the goal of code reuse. And this is in modern days where the code injection, like shell code injection, stack smashing, is no longer feasible, which I'm going to explain later. And so you have to reuse existing code in the process memory. And so you have to figure out what kind of versions and what's the operating system, the application. And so that's reconnaissance. And if you look at the advanced persistent threats, and they all follow this kind of process. And then you try to get hold of vulnerabilities, including a leaked pointer where you can decode the randomization, reverse the randomization. You have other vulnerabilities that you obtained, and then the execution, where you launch the payload, you chain the gadgets together, you launch the payload, and then depends on your attack goal. It could be lock the screen, lock the file system, the ransomware, or command and control, and use the machine to collect information. And so there are multiple steps, and then each step has different requirements. And a lot of times that we focus on the central operations that's really shared by a lot of exploits, and regardless if it's Windows or Linux in the specifics, but then the concept is very similar. And for example, you need to have a memory disclosure because modern systems have at least a coarse-grained ASLR or position-independent executables, which we're going to explain later. And you have a code pointer or object pointer where you have be able to decode the other code pages. And then you want to have some access to system calls or function calls, and so that you can and be able to chain together certain operations to satisfy your needs. If you look at the right-hand side, and this is a tree that we put together that talks about different attack conditions, ACs. And the ACs really depends on the kind of defenses the system may have. And so if you have a control flow integrity, if it's well reasonably implemented, then you defend a lot of control flow attacks. And of course, you're still vulnerable to data-oriented attacks, data-oriented programming, which we'll explain later. And if you have say fine-grained ASLR, where say you have a function level re-randomization, and then you may have randomization periodically re-randomized every 60 seconds, or I mean every 60 milliseconds probably, then you defend against a lot of attacks. But then if your randomization window is too big, if you wait for too long to re-randomize, then the attacker will have some time to figure out the layout of your process memory and be able to attack. And then this is, if you look at the return-oriented programming, the basic one won't be able to be useful, but then the newer one, just-in-time return-oriented programming, would be, let's see, would still break the fine-grained randomization. Okay. And so stack smashing, which we talked about in class, in school, also, most of the time is no longer feasible in practice because of all the existing defense mechanism. Microsoft call it data execution prevention, DEP, and some people call it WX or X or no execute. And either way is that basically say if you can write in the memory space, then you cannot execute. And so stack cannot have executable code. And so that's why the code reuse is very much in fashion. And it started from return to libc attack, which came out in the late 90s, and then in 2007, return-oriented programming was discovered, and that's really just ignite a whole host of different flavors of return-oriented programming or its variants. And the one that we'll focus on talking about in some of Salman's discussion is called just-in-time return-oriented programming, where it's specifically target fine-grained ASLR, address-based layout randomization, and it has this ability of dynamically discovering the code pages, and not having to worry about specifically where each gadget locates, and then still be able to chain the gadgets together and put together an attack payload. And so this is, from the attack side and the defense side, this is still very much active topic, the how to defend and code reuse and how to come up with new code reuse attacks. And in terms of address randomization, which is a big defense against the code reuse, and because if you distribute the code in a random space, then it's harder for attacker to reuse code. And the concept of this, the first research paper on memory randomization was published in 1997 by Daphne and her colleagues. And after that, there has been a lot of demonstrations of different flavors of it, starting from the Linux PAX project in 2003, and up until a few years ago, the ILR and ZipR is at instruction level randomization. And we also have seen register level randomization, and so those are very fine-grained. And of course, it's as long as you know how to reverse the randomization, you'll be able to execute your instructions. And of course, it takes time, a little bit overhead, and then you don't have to do it just one time. You can do it continuously. One time after a little bit, you redo the randomization to make it harder for attackers to find where a code is. And here, just very quickly, I want to show what is fine-grained randomization. On the left, it shows the, I apologize, it's coarse-grained randomization. On the left-hand side is without PIE. On the right is with PIE. PIE just says, okay, you're executable. Every time it runs, it will start at different location. And then different components, different segments, library, and so on, text and data will start at a different location. And so the coarse-grained with PIE is stronger. And here we have some illustration and shows that within the process memory, and everyone will have a different order of the different segments, stack, library, text, and so on, data region. And so this is still coarse-grained with PIE. But then fine-grained, it says you don't have to stop as if you have a stack, it doesn't have to be sequential, even though its starting point is different. The internal bit can also change the function, basic block and instruction can also be randomized, as illustrated here. So it takes more time to randomize and then you have to have more bookkeeping information so that you can reverse the mapping, and then making it harder for attackers. And then the paper that we'll talk about, the research that Kevin Snow and Fabian Morose and his group demonstrated the just-in-time return-oriented programming that breaks the fine-grained ASR. And then Salman will talk about the specific context and our measurement results. And so this is, Salman will go next with a demo, and then Long will talk about data-oriented programming, and Hans will do a demo on the DOP. Asokan will talk about hardware-assisted protection, and so that's basically our structure. And feel free to, I'll stop controlling Salman's window. Stop controlling Salman's window.
Yeah, I think I got it.
Okay, yes. So someone can take over, and everyone feel free to type in your questions.
Yeah, thank you, Professor Yao. So I'm Salman Ahmed. So basically in this portion of the tutorial, I'm going to talk about the code reuse attack and its particular flavor, like the return-oriented programming and just-in-time return-oriented programming. Then I'll show you a demo about how we can get different kind of gadgets, and then how can we measure the time that we need to obtain different kind of gadget set. And then I'll also demonstrate what happens if we start the gadget searching from multiple locations. So a little bit about the code reuse. So basically, we all know that attackers can no longer inject the shell code because of the NX or DEP policies. But what they can do is they can still utilize some executable code from an application address space. So basically, that's the code reuse attack. But that's not the interesting part. The interesting part is how they use the code. They utilize the existing executable code, because there are different flavor of it. And as Professor Yao mentioned, it started from 2007, and like ignite the whole world to use different technique. So I'm going to particularly show you two different techniques. One is the most widely exercised. One is the return-oriented programming. So the way this return-oriented programming works is it utilizes short instruction sequences followed by a return instruction, and only those that has some specific purpose. So different kind of these short instruction sequences can do different kind of smaller tasks. And these short instruction sequences usually called gadgets. So now once attackers chain these smaller things together, they can usually perform like some big thing, usually some malicious goal. And it can be as expressive as the Turing complete operation. So we know that the Turing complete operation has 7 key operations, like the assignment, load from memory, store to memory, jump, logical operations, system operations, all these things. So these gadgets can do all these things. So not only these Turing complete operations, it can attackers utilize these gadgets in different contexts, like bypassing some monitoring tool or to do some specific things. So we compile all these gadgets and put it in our CCS paper, so you can free to check our CCS paper to get all this information. And to just give you some idea about how this code reuse attack actually mapped into some real world attacks, we are going to give you some idea about an existing exploit, which exploits the on-found vulnerability of Adobe Reader. So as Professor Yao mentioned, the exploit is not only code reuse attack. It has different components. The code reuse attack is just a single component of it. It needs to have some technique to control the stack. It needs to have some technique to access the system function, because if the attackers want to interact with the system, it needs to go through the system APIs. So in this particular exploit, it does the stack manipulation using the unlimited out of bounds vulnerability in the casting program on the on font thing. And the code reuse part is actually, it uses some ROP gadgets. And for the system function, it uses these system APIs to do different kind of things. Now, this particular technique here is pretty much like the stack manipulation is pretty much ad hoc. So it's very difficult to protect that part, but it's pretty much generic to protect the ROP gadgets. And that's what we see the address space layout randomization. So basically the coarse-grained address space layout randomization can relocate these gadgets at different location in a different run. But the problem of this coarse-grained ASLR is that if we have a memory leak or address leak, all the location of the other gadgets can be deduced from that single leak, because all of them are relatively positioned with a gadget. And if we know the position of a particular gadget, all the other positions can be known. So to protect this from happening, researchers proposed the fine-grained ASLR. So basically, the key thing is on memory leak is not now enough. You need to have like multiple memory leaks to infer the location of those gadgets. So which is very good thing, because it can protect from all the basic ROP attacks, which are preferred offline and depend on a single memory leak in order to execute. So now the thing is then, since the fine-grained ASLR can protect from single memory leak, like all the code reuse attack now impossible with the fine-grained ASLR? The answer is no, because there are some advanced attack, as Professor Young mentioned, like the just-in-time return-oriented programming, which can work with the fine-grained ASLR. So what that means is, since it can work with the fine-grained ASLR, that means it can utilize a single leak and can repeatedly leak to explore the gadget as long as it needs. So which is pretty like powerful, because it has the flavor of the, it has the dynamic flavor, and it can work on the fly to construct its exploit payload. So what's the fundamental difference between just-in-time ROF and the basic ROP? So the fundamental difference is how it explore the gadget space, like how it look for gadgets. So basically that is the memory de-randomization part. And basic ROP, as I said, the basic ROP attackers prepare all the gadget chain statically and offline, and depends on some single memory leak to readjust all the other addresses of the gadget. But when we have the fine-grained ASLR, this is no longer possible. We need to compute each of the address of all the gadgets that we need to prepare our gadget chain. So that's what makes the JIT ROP apart from the basic ROP. And it does this by looking into the code pages in a particular way. That thing is called the dynamic code harvesting thing. So basically, both basic ROP and JIT ROP start with a single code pointer leak or address leak. So in this figure, if we consider this 0x on F95C4 as the address that has been leaked, then what JIT ROP's dynamic code harvesting process does is it look for the mapped code page for this particular address. For example, here the mapped code page for this particular address would be from like F900 to F9FF, which is a 4 kilobyte kilobyte code page. So once it finds this 4 kilobyte code page, it can read all the content in that code page and look for the opcode for call and jump. And it can, when it finds the call and jump instruction, it can look into their targets. So those targets can be another memory leak. So how? Because then that particular address can be also used to read other 4 kilobyte code page. And when we read that other 4 kilobyte code base, we can get more call and jump instruction. And this process, we can also, since we can read the code bases, we can get the return-oriented programming gadget, like ROP gadgets from these code pages. So this process like recursively does this memory leak and look for the gadgets that it needs for its exploit. So this is how like a single memory leak can be turned into a repetition of memory leak. And since this process does this dynamically, even if it's ordered differently, it doesn't matter because it looks for what it needs. So certainly this GitRub is a very powerful attack technique, but there are still some in-depth questions that needs to be answered. The first factor is time. Like if this gadget harvesting thing takes forever, like let's say more than 5 seconds or more than that, then some other monitoring tool can capture this process and terminate it. So if it takes long time, then it's not that useful. But if it takes like very small amount of time, then it's useful. But we need to know what this time is. So that that particular aspect needs exploration. But another thing is we know that GitRub can circumvent fine-grained ASLR, but there are different flavors of fine-grained ASLR, like functional level, block level, instruction level, register level. So the question is, does it make all these techniques useless, or there are some other policies that is still good? So we need to measure that aspects as well. And the last thing is the JIT ROP start from a single code pointer leak. So what happens if we change that starting location? Like if this process starts from different location of an address space, what happens? So we need to answer these questions, and we have discussed extensively these aspects in our CCS paper, but I'm going to give you a brief overview of them here. So the first thing is attackers really need very little time, like a few seconds, less than 3.5 seconds to do this exploration. And to do this, we have used different kind of gadget set, which over approximate the attacker's capability, but sorry, we underestimate the attacker capabilities, because sometimes attackers can just need a few things to complete their exploit. But in general, it take like less than 3.5 seconds to complete their exploration or to find what they need for their exploit. And the second thing is not all the schemes are useless, because we find out that the instruction level randomization can block up to 90% gadget and can restrict the Turing complete operations. So this instruction level randomization is still good and can prevent JIT ROP. And the next thing is we found out that the starting location has no impact on the connectivity. That means it can explore multiple code pages regardless of the starting location, but it has some impact on the time, like how soon or how fast it can explore these gadgets. So the fundamental reason is that there are certain code pages in an application address space which are dense and contains diverse set of gadgets. So when the code harvesting process or the gadget searching process lands those code pages sooner, it can get particular set of gadgets quicker. So we have a question in the chat. Should we answer it or wait for the last minute? Okay. So the question is, when we have the target addresses, like the target address of call and jump, so to read out the question, like how reading the content of on code page gives you the addresses to explore, but how does the attacker who has no control of execution yet managed to read other code pages. So when the code harvesting process starts, it has access to all the code pages, like not only a single code pages. Like I'm talking about the permission, because even though we are reading a single code pages, and that like target is, it needs to be the mapped region. If it's mapped outside of the process address space, then yeah, it can they cannot read that that particular thing. But so when we talk about the process level, all the attackers or the process will have access to all the mapped code pages. And usually these mapped code pages are enough to get all the gadgets they need to complete their exploit. Okay, so then we saw that to protect programs from memory leak, we have the fine-grained ASLR, but now we see the fine-grained ASLR can be also circumvented using some advanced technique. So the question is it protecting code reuse attack is impossible? The answer is no, because of the control flow integrity, as Professor Aya mentioned, but it has its own set of limitations, especially resolving the indirect target branches, which is a pretty like, so far it is not that precise to like deploy in the real system. So that's the theoretical aspects of what I wanted to cover. Now this is the demonstration part, and we have this slide in the very beginning of this presentation, and I have also put this in the Slack. So basically this slide has the setup part, like how we can set up to see some of the hands-on. So basically to install the Docker, and we have packaged everything together in a Docker image. So in our GitHub repository, we have the Docker file to do the setup. So I'm going to show you like briefly of this setup, and then I'll show you some results. Okay, so when you clone our repository, you will have something like this. We have a Docker file here. Once you have this Docker file and you are in this directory, you can just simply go ahead and issue this command here. That will build your Docker image. And so the prerequisite is you have to have the Docker installed. So it will do all the setup for you. So I have already issued this command before, so it takes less time for me, but for your case, it might take around 1 to 2 minutes. So once you have that, you need to run your Docker image by issuing this command. So if you issue this command, it will go into that particular Docker image into this directory, which is tutorial SecDev 2021. So inside this directory, we'll have the same thing, but all these things have been compiled to make it make the Git drop program to just use instantly. But before using the Git drop program, let's go to the next slide. And also all this instruction we have all this instruction in our SecDev, so in our repository, like if you go to this repository, we have all this information. So you can follow this on this page, from this page as well. So we need to run some program to search the address space of that particular program. So here we are going to launch this Nginx server. So if you issue that particular command from here, the Nginx server is running, and we intentionally leak a single code address from the Nginx server. But in reality, this needs to be done through some other vulnerability. To make things easier, we just intentionally leak this this address. Now the next command is you have to issue the gtrop program with -p, which is the process ID of the Nginx server. To get to the process ID, you can just simply issue this command here. That will give you all the processes like the Nginx server here. And to use this gtrop program, just copy and paste this command. And you need to change the PID here. So you can give the master process PID, which is 18. And this leaked address here, change this address to this leaked address. So this command will look for all reachable code pages and look for the gadgets, the Turing complete gadgets in those code pages. So sometimes you need to like issue twice because the address space may not ready yet to search for. So it's now searching different code pages. All these addresses are the address of a code page, like starting of a code pages. So it look for these code pages, searching for different kind of gadgets, and finally it will show, the process will show you different kind of gadgets and how many of those gadgets are. So as you can see, the LM means load memory, SM means store memory, LR means load register. So different kind of gadgets. We have all this information in our paper. If you are interested, you can look details of this name there. And this is the number of gadgets that the process found by exploring all the code pages. And you can get some other kind of gadget set, like if you issue operation 7, like 07, then you can get, it will do the same thing, but it will look for different kind of gadget set. In this case, it will look for the memory move Turing complete gadget set. So it look for move Turing complete gadget set in all the code pages. And it will show a similar kind of statistics, like how many different kind of move Turing complete gadget sets are there in the address space. Yeah, so these are the gadget set for the move Turing complete gadget set. So you can see the move TCMR has like 10 of these gadgets. So this name has like a particular type of instruction. You can find this information in our paper as well. So then the next thing is how we can get the, we can measure the time. So so here we have the instruction for operation on. You can get the time to get different kind of Turing complete gadget set, operation 2 priority gadget set, 3, 5. So the numbering is a kind of odd, but like on 2, 3, and then 5, because I used 4 for something else. But you have all this information in the GitHub repository as well as here. So if you issue like operation on here, then you can see the Turing complete gadget has total of 11 gadgets, and it looked for, so far it found 10, 11. So it takes around like 8 seconds for a particular starting location. Sometimes it will take less than 8 seconds for find all the 11 gadgets set. So here it takes 10 seconds, but it will look for this in the address space from starting from a different locations. So this process will take like maybe 2 or 3 minutes. So I'm not going to show show it to complete. For example, here you see that it takes like around 6 seconds to find all the 11 gadget sets. So it depends on where we start. As I said before, it has an impact on the time. So I'm going to stop this process because it will take time to explore everything. And the next thing is, if you can follow along with this thing, then you can manually change the starting, like initial memory leak. For example, in our case, the initial memory leak is like this address, but you can manually change it, let's say, on to, let's say, 7. That will still like will give you some other gadgets here. If we do the Turing complete gadgets, I think this page does not has, let's say 3, not here. Okay, so you can just change it to different address to see the impact. So that was the exercise, but if you can follow along, you can do it. But I think for the sake of time, we might stop the demo here. And actually, this is all from me. So our next presenter is Professor Long Chen. He will talk more about the data-oriented part, data-oriented attack using some sort of data manipulation. So I'm asking Long to take over. And if you have any questions regarding the tutorial, regarding the demo, just feel free to like put your question in the Slack or in the chat. We'll try to answer as our best.
Okay, thanks, Salman. This is
let me give you the remote control. Yeah.
Okay, thanks. Hello, everyone. This is Cheng from the School of Computing at Clemson University. Before I joined Clemson University, I was working with Professor Yao at Virginia Tech for my PhD study. In the next around 10 minutes, I will briefly talk about data-oriented attacks. Yeah. So as Salman discussed, those return-oriented programming attacks, ROP, or just in-time ROP, those attacks are of the control flow hijacking attacks. Basically, they change the control flow of the program execution. However, launching those control flow hijacking attacks are becoming increasingly difficult due to many deployed defenses like the control flow integrity enforcement. Because of this reason, non-control data attacks, also known as data-oriented attacks or data-only attacks, are considered as an appealing technique for system compromise because they are more stealthy. They can change the default behavior of the program without violating the control flow integrity. So this is a history of the data-oriented attacks. Although such attacks have been known for a long time, as you can see in 2005, the first paper, non-control data attacks, have been published. Only recently, those attacks, data-oriented attacks, attract more attention. So researchers from different groups, they have shown data-oriented attacks can lead to serious security problems of many real-world applications. For example, the Chrome, IE, different web servers. Interestingly, attackers may exploit the data-oriented attacks to undermine the control flow integrity protection, which makes the control flow hijacking attack possible. In particular, two advanced techniques to construct the data-oriented attacks have been recently proposed. One is called data-oriented programming, DOP. The other one is called block-oriented programming, BOP. I will briefly talk about these two advanced techniques. So we classify data-oriented attacks into two categories. The first one, we call it a direct data manipulation, DDM, refers to a category of attacks where attacker directly manipulates the target data. Those target data can be some security critical decision-making data or some identity data in the memory space. The second type of data-oriented attacks, we call them as a data-oriented programming attack. So it's kind of similar to the ROP, return-oriented programming, in terms of they all use reuse some code sequences, which are called gadgets. In DOP, those short code sequences are called a DOP gadget. The attacker basically reuse those gadgets, chain them together in a particular order for malicious computation. Different from a DDM, in DOP, attackers indirectly manipulate those data by using those existing gadgets in the memory space. The BOP, block-oriented programming attack, is kind of similar to DOP. The main difference is that it operates at the basic block level. So that means that each gadget in BOP is basically a basic block. So next, I'm gonna show some simple examples about those data-oriented attacks. So the first one is a simple DDM, a direct data manipulation example. As I mentioned, those local variables that are used for decision making or represent a user identity can be attractive target of attackers. So in this example, this PWUID, this variable represents users UID. The different values of UID can have different permissions. So suppose in line 2, there is a format string vulnerability, which allows attacker to manipulate the value of this PWUID. By exploiting this format string vulnerability, if attacker can change the value to 0, so it's possible the attacker gets the root privilege. So next example, we show that data pointer can be a target of attacker in DDM attack. So this PTR is a data pointer. By manipulating the value of this PTR, so that to let it point to different areas in the memory space, it's possible attacker can observe the memory content in different areas to infer the knowledge about the address space layout. So attackers can use this, exploit this vulnerability to bypass the address space layout randomization scheme. So next, I will show an example about the DOP attack. Compared with a DDM attack, DOP attack is more complicated. As we know, it allows attacker to perform arbitrary computation in the program memory by chaining those DOP gadgets. It involves multiple gadgets, and it requires to attacker to stitch those gadgets together in a specific order. So it's more complicated. Okay, let's look at the code in the left. So this code snippet models a very simple FTP server. So this server program takes input from the remote client. When receiving a packet, it checks the packet type. So we have different types here, and then it does the different processing. So suppose in line 7 here, read data. This is a vulnerable function. It has a buffer overflow vulnerability, which allows attacker to corrupt this local buffer here. In line 3, this is a local buffer. So in addition to corrupt the buffer, at the same time, attacker has a chance to manipulate or corrupt the other local variables close to this buffer. So assume the attacker's purpose is to calculate a value. The value a plus b. So intuitively, we want to find a gadget in the code which performs the addition calculation. So luckily, with in this while loop in line 13, we get addition gadget. So this addition gadget can be used to calculate the value of a plus b. So the next thing is we want to let this size is an integer pointer. So the next thing is to let this integer pointer size point to a value a or b. Yeah, and the next step is to assign value a or b to this served total. Yeah, so that means to launch this attack, we need multiple steps. Here multiple steps means attacker needs to send multiple attack payloads to the server program. So in this example, it requires 3 rounds. In round 1, attacker send a malicious payload to corrupt the local buffer and the type, and also this pointer's SRE, so that let the pointer size point to value a. So in the second round, by sending another malicious payload to the server, attacker let this assign value b to this served total. So the third round is pretty straightforward. We just execute the addition gadget in line 13, so we get the value a plus b, and this value is stored in served total. From this DOP example, we know that typically a DOP attack involves multiple data-oriented DOP gadgets, and those gadgets should be executed in a particular order.
Hey,
So
Long,
next,
we have a question for you here.
Yeah. Sure, please go ahead. But where is the question in Slack?
No, in the chat. Let me read it out for you.
Oh, I couldn't see it. I'm sorry.
Oh, sorry, it's not a question, it's
Yeah.
a comment. So yeah, you can go ahead.
Okay, sounds good. So this figure shows the idea of the BOP attack. As I mentioned, BOP operates at the basic block level. So each gadget basically is a basic block in the program. So suppose attacker wants to execute this three statement in a particular order. You see statement 1, 2, 3. So to construct the BOP exploit, the next step is to check those basic blocks to see whether those basic blocks contain some of those statements. If a basic block contains some of those statements, we call it as a functional block. So we will find many different function blocks in the binary code. So, but those functional blocks are disconnected. So we need to find a execution path, from the entry point to the exit point that can connect to those different statements. So we need a dispatcher blocks. Those basic blocks that connect to connected functional blocks are called dispatcher blocks. So in this BOP paper, the authors also presented a efficient program algorithm, to search such paths that contain all those required statements in this particular order. All right, so okay, so we know DOP or BOP attacks are powerful. They can be used to construct an expressive, exploit. However, it's non-trivial to, construct such attacks because teaching those CFI compatible gadgets is challenging. It requires memory write primitives to teach those gadgets, and typically it involves multiple steps. It could involve like 1,000 steps, so it's less evasive. Suppose if there are some anomaly detectors, they can be easily detected. So till now, it's very, we haven't found an efficient way to automate the whole process of generating end-to-end DOP or BOP exploits. As to the defense, DFI, data flow integrity, can be used to defend against data-oriented attacks. However, it incurs a high overhead to track the data flow at runtime. So Hans will talk about later. Hans will talk about some hardware-assisted defenses, which can be very efficient, to defend against the data-oriented attacks as well as control flow hijacking attacks. All right, so I saw a question in the chat window. Yeah, that's a good question, Brian. Yes, so actually there, when training those gadgets, it's possible. Yeah, it's possible to incur some side effects. For example, it changes, some other behaviors of the program execution, or it may generate some side effects. Like some cache pattern or whatever. Yeah. So one challenge to construct such a DOP or BOP attack is to how to avoid those side effect. Yeah, this is a really good question. Yeah, thanks. Next,
just to add along, in our SEM tops paper we have this. We measured this side effect in some extent, right? So they can also go to that paper to read details.
Yes. Yeah. So Dr. Yao has a question about the BOP compiler. Yeah, BOP compiler automates the attack to some degree, but it's not the fully automation process. Yeah, still, this is a challenging problem. All right, so next, my colleague Hans will show a demo about the DOP exploit. Yeah, thanks. Hans, please.
Hans, do you need to share your screen?
Yes, I hope that I'm sharing my screen right now.
Oh, yeah, you are sharing. Yes, that's right.
Okay, So I'm going to start by showing a brief demo of this original DOP attack by Hu et al. Um, so we're going to use the same Docker environment that Salman already used, and then we're going to use the original VM by Hu et al. So you can find the instructions in the DOP folder in the same GitHub repository as used by Salman earlier. So I'm hoping that this will kind of show you how to get started and get the attack running, and by that you can then also kind of do a more deep dive and look at the nitty-gritty details of how this attack actually works and what kind of exploits it uses. The goal of this is to kind of better understand all of these smaller details, which then allow us to make kind of reasonable trade decisions when we don't have to do trade-offs between what defenses to deploy in practice. And also, of course, to also think about how to design new defenses to defend against these kind of exploits. So as mentioned, we're going to use the essentially replicate the attack from the original paper. There's quite a lot of more details in our paper, this later paper here. This README that I'm looking at here, this is in the repository in the DOP folder, so you can find all of these links in there. So to go back maybe and look at what the attack is. So this is an attack against the Pro FTP server. The goal of the attacker is to leak the SSL private key of the server. In a sense, the challenge for the attacker here is that the server is going to, not server, the key is going to be somewhere in an unknown address on the heap. But what the attacker can figure out is this initial base pointer, which is to an SSL context, and that contains one pointer to another structure and along to another structure and so forth. So the attacker wants to be able to use DOP to read this one pointer and dereference multiple times in order to get the private key and extract it. So how is this actually done in practice then? So what this attack does is it uses regular FTP commands to create new directories and files on the server. Specifically, it will create these new folders with very specific message files. And these message files are kind of these hello messages that when you get into a folder, these will be parsed and displayed to the user. The problem here is that these messages can contain special characters that will be parsed by this sReplace function in order to show something like, for instance, the server name, the current date, or something like this. And it so turns out that the sReplace function does have buffer overflows that allow this message to be constructed such that the attacker can control what happens in the program. So you can find the function itself in this Pro FTP folder under the Dop directory, and here you can take a look at the specific function. But there is essentially an off by one mistake in this function that allows the string terminator to be replaced such that the overflow can happen. Okay, so how we're going to do this attack is we're going to use the original VM for the DOP attack. And the reason for this is that it is dependent on very specific versions and very old versions of Pro FTPD and libraries. So it's very challenging to kind of replicate this in a Docker environment. So the victim program itself is going to run in the VM, and then we're going to run the exploit in the same Docker container used by Salman earlier. You can find through this link, you will find some instructions on how to set up the VM. I will assume that it's kind of set up here, and you can set it up on your own time. This is requires a bit. This is a bit tricky because you need to network them such that the Docker has network access into the virtual box. But by following these instructions, you should get that running. So once we have this done, you can either what I have done here is set it up so that I can SSH into the server. This is on the right here, but you can also just as well use the virtual box GUI to do it. So you can also just log in here and replicate the steps in here. So I will, in this instance, I will assume that the version, or in my configuration, the VM is going to have this address. So this is what I'm going to use. But obviously, in your case, you will have to change it if you have different addresses. So the first thing we need to do is of course, start the server. We're going to attack. And then at this step, we're going to do a slide sheet. In practice, what is needed for this attack is an address that is writable, and such that the address itself doesn't contain any 0 bytes, because we're going to inject this address using string manipulation. And if there's a 0 byte, it's going to be a string terminator that prevents this. So in practice, the attacker would actually just guess this. But in this case, we're going to cheat and use GDB to figure it out. So this allows us to connect to the GDB instance, and then we can just look at the memory layout. And what seems to work most of the time is the libcryptos data section. So we can take this address here, and as we see, there is a 0 byte at the end, so we will replace that with a 1 later. So the next step would then be to start so now I realized that I had renamed this, but you can just reuse the same Docker instance as Salman used, but I have used a different name. The only thing you need to do is that when you run it, you need to also set it up so that the host machine is exposed, or the network is exposed, so that we can actually connect to the VM. And here you should also already have this MSF console installed, which will launch Metasploit, where the exploit is going to be executed. And then we can take these commands and execute them in the console. The first one is going to load the exploit, and the second one sets some parameters. The first ones you don't need to touch, but these you should update if you have a different kind of network setup. And this final thing here is going to be the memory address that we just figured out. So then let's take this one. So provided everything now went well, we should be able to run this. So one thing to do is exit the GDB here, or just continue execution. Let's quit it for now. If you replicate this might fail because there is still some randomness with choosing these addresses. So if that happens, the easiest way to fix it is simply to just kill the pro-FTPD instance and restart the attack, and that should get you get this working. And eventually, if it works, you should see something like this. And now, if all went well, this should be part of the private key of the instance. So we can use this command here to take actually a look at the specific key and see if what we get is matches. So we can see it's the private exponent, and we can also compare it to this one and see that we actually managed to succeed with this attack here. These are in reverse order, so the A1 is here and it's at the end here. Yep. So this was the attack itself. So going on, we can kind of start thinking about what were the steps that the attacker needed to kind of achieve here. So the first is that the attacker needs to know something about the memory layout. So this one address, of course, we just guessed. So this we got that way. But it also needs to calculate the various offsets, because we do these dereferences, for instance, of the data structures. And to do that, we need to know at what offsets we find the pointers in the data structures that we have figured out. And this is where I encourage you to also kind of continue and do a bit of exploration on yourself. So what you can do is follow these steps here to kind of replicate the attack. And then the exploit itself, this is relatively, well, kind of easy to read in a sense, because this is just Ruby scripting that is very easy to go in and edit, and you will find in this exploit code, you will find a function that is exploit, and this is the thing that runs the whole thing. And here you can see various functions it calls, and all of these are now essentially gadget that it invokes. And what you can do here is easily go in, for instance, comment out one of these, which will print you a marker so that you know where the attack is going, and then it will stop execution, which means that this left side here, the Metasploit will actually pause, and at that point you can again connect the GDB and, for instance, look at the memory and see what actually happens in the memory space of the program. Yeah, so if we take a look at this exploit, we see that there are lots of these kind of offsets calculations here. So for instance, here we have the SSL context, and we need to know that the specific pointer that we want is at this offset within the structure itself. So this means that the attacker then needs to know, it needs to guess or somehow figure out some of these addresses, and then also, for instance, analyze the binary to figure out what the correct offsets are needed for this attack. The other thing is that this attack requires a kind of dispatch loop and a gadget selector. So in this case, that we don't have a dispatch loop as such. It's just that we can actually repeat the commands and send multiple FTP commands to just do the sequence of instructions that we need. And the selector, in a sense, is the overflow that happens in a S replace that allows us the attacker then to choose what actually happens. And then obviously we need to find the gadgets. So thinking about this, we can then kind of start thinking about how could we prevent these DOP attacks. So the obvious kind of answer is that we just make everything memory safe. We don't have any memory errors, everything is fixed, and we're done. So the other solution here is hiding information. But as Salman already explored here earlier, that's very tricky to do kind of efficiently enough that it can't be circumvented using modern techniques. And then the third option here could be just protecting the critical data. So what's the thing that the attacker needs to actually corrupt for these attacks to work? So memory safety itself, that's quite a big kind of task to get full memory safety. With formal verification, we can get pretty close. So that gives us quite good assurances that the program is actually free of memory errors if we can do formal verification. But it requires considerable effort. So it has been done for cryptographic libraries and for the SEL microkernel and things like this, but it's not really, in a sense, doable for all the code that is out there. So this is not practical for everything. So another approach is to use runtime protection. So you apply some protections that prevent some types of attacks. And the problem here is that, like we saw earlier already, these are typically partial. So they protect against some attacks, but they will not prevent all. And then the more kind of ambitious they get, the more they often also then impact performance. So there is kind of a tricky trade-off here. So hardware assistance here helps, because that allows you both to get these defenses to be more fast, but they also can allow these defenses to be more secure. But this also isn't necessarily a panacea, especially if you consider legacy code or something like this. Even if you have some of the newest hardware, that might not, the legacy code might fundamentally not be kind of workable with that. So then we have this randomization, which Salman already kind of demonstrated that at ASLR, and even with some re-randomizations, you can still break these kind of randomization techniques. Another issue is that this might not necessarily be effective against all types of attacks. For instance, in this DOP attack, we already saw that it actually uses legitimate pointers and dereferences them to figure out, to find the data it needs. Again, here is again hardware assistant kind of upcoming, and there are some interesting schemes that do quite a lot of obfuscation of the address space itself, and not just moving things around a bit, but they kind of obfuscate the addresses themselves, which make it much harder. So I encourage you to take a look at this Morpheus paper, for instance, which is an example of these developments. And then finally, we have this idea that maybe we can protect the kind of critical data here. and the kind of obvious target would be pointers. So for any kind of control flow attacks, you typically need to modify some code pointers or return addresses or something like this to achieve what you want to do. And then for at least for known DOP attacks, all of them require that you are able to modify some data pointers. So if you can protect both code and data pointers, we would get quite far. And again, hardware assistance is kind of making inroads here. Intel CET is upcoming, that protects code pointers, or essentially the exploitation of code pointers. And then we have ARM pointer authentication, which is also specifically designed for protecting code and data pointers. Here I will pass on to Professor Asokan.
Thanks, Hans. Maybe I can continue by requesting remote control from you.
Let's see if it works. This is in a VM also.
Okay, otherwise we can go back to Salman sharing it.
I can share it. I have already set it up.
Okay, so then let's go for that. So thank you everyone for staying this long. Unfortunately, I'm not on Slack, but if you ask questions in Slack, Hans is on Slack, so he can answer. But if you ask questions in chat, I can answer. Do I have control?
Yeah, you have now control.
Okay, so so I'm going to talk briefly about hardware-assisted defenses. I think Hans already alluded to some of them. And the setting for this is that we want to protect against these runtime attacks that arise because of the attacker being able to exploit memory vulnerabilities, but we want to do that without incurring a significant performance penalty. So Hans mentioned that some of these defense techniques like control flow integrity and so on, they have this inherent tussle that either you get sort of a coarse-grained level of protection, which means that you don't get ironclad security, or if you try to have like a fine-grained level of protection, then the overhead of doing that in software can be too high. So this is the setting for thinking about hardware resistance and how can we use or exploit the availability of hardware resistance to break this tussle between level of security and cost. And but in general, I mean, you can design either new processors or process extensions from scratch. And some of the examples that Hans mentioned earlier are like that. And they can give a very good level of protection cheaply enough, but deployment can be a challenge because any new changes to hardware will require the cooperation of process manufacturers and so on. On the other hand, what's been happening recently in the last 5-6 years or so is that hardware manufacturers, processor manufacturers have been rolling out different kinds of protection mechanisms for various purposes. And there's like a whole menu of them. So Hans already mentioned some of them, point authentication in ARM processors, CET, control flow enforcement technology in Intel processors. But these are just two examples. There have been many others. And this is why looking at these mechanisms that are already being rolled out and see how they can be used for more effective protection or expanding the scope of protection is an interesting research topic, because it sort of breaks this, not only does it break the tussle between the level of protection and cost, and being able to provide both like high level protection at a low enough overhead, but do so without having to tackle this deployment hurdle because these are being rolled out by different manufacturers. So today I'm going to just briefly talk about point authentication. Given the amount of time, I can't go into detail, but I'll give you some pointers where you can look for more information. So point authentication is a recent addition to the version 8.3 of the ARM architecture. It was announced, I think, like 2 or 3 years ago. There are specifications that give you the details about that. But essentially, you can think of point authentication as consisting of 2 parts. There are new processor instructions that allow you to create an authenticator given a pointer and then verify the integrity of a pointer by checking the authenticator. So that's one set of instruction. And these authenticators are cryptographic transformations, and they make use of a key. So the other part of point authentication is how to manage this key. And then the goal is to sort of provide a hardware primitive that approximates pointer integrity. And I'll come back in a minute to talk a little bit more about pointer integrity. But intuitively, what that means is that if a pointer that is in the memory is changed by an attacker by exploiting some memory vulnerability, we would be able to detect that afterwards by making use of these pointer authentication extensions. So, like I said, the specification was a few years old. It's been revised continuously. There are compatible processors that are already in the market from Apple, but this is part of the ARM specification. So presumably other manufacturers who make ARM processors will follow as well. This hasn't happened, which is a little bit surprising because it's been some number of years. Apple is the only process manufacturer, as far as I know, who has point authentication in their processors, but it is part of the ARM standard. So how do they achieve point integrity? So essentially, point authentication makes use of the fact that when you're going to use a full word to store pointers. So it's a 64-bit word, but pointers themselves, depending on your configuration, the addressable memory is something like corresponds to say 40 bits. So even if you store the pointer information in the word, there are some unused bits in the word itself. And the idea behind ARM point authentication is to compute a pointer authentication code, which is essentially a message authentication code, a cryptographic message authentication code, and store that in these unused bits. So how is this pointer authentication code computed? It's like I said, it's a message authentication code, which will take the pointer as the sort of plain text input, the point authentication key as the key, which is then managed in some way. But in addition, and then compute the message authentication code and put it in the result. But instead of just using a straightforward message authentication code, point authentication uses what's called a tweakable MAC. The tweakable MAC, you can think of this as something that a message authentication code function that takes an extra parameter, which is called a tweak in cryptographic terminology. In point authentication terminology, it's called a modifier. And you can think of that as like a message authentication code is a mapping between input and message authentication codes. You can think of a tweak as something that induces a family of such mappings. So for the same key, without changing, if you change the modifier, you get a different mapping each time. So this is a way to sort of diversify the way in which a message authentication code is computed. In the case of point authentication, this is used to capture the context. So you can sort of use the same key, but capture different context by using different modifiers. So I mentioned in the beginning that pointer integrity is memory safety for pointers, which is essentially ensuring that pointers, if they are changed in memory by the adversary, we can detect that. And you can see why this is useful. So consider a function like this. And in ARM, if this is not a leaf function, then whenever this function is entered, the return address for this function is stored on the stack so that you can go off and call the other function, the nested functions. But this is where the attacker can now go and change the return address that's stored on the stack. So if pointer integrity is in place, then at the point where this return address is reloaded from the stack, we'll be able to verify this integrity. And you can see how this might work. If there's a message authentication code in the form of a pack, we would compute that when we store the return address, and when we load the return address, we'll check that the code is still valid. So the attacker can no longer just fabricate arbitrary pointers or change arbitrary pointers because they wouldn't be able to compute the correct message authentication code. This is intended originally for specifically for return addresses. So ARM and Qualcomm have a white paper that showed how you can do return address protection, but presumably, conceivably, you can see that this is a powerful primitive. You can use it for other things as well. So given that it's a primitive, you need to decide two things, right? So you need to decide when are the pointers packed and unpacked? When are you going to compute the authenticator? And when are you going to verify that the authenticator is correct? And then you need to decide what is the modifier. So ideally, the modifier should be unique. Every time you compute a pack, it should be unique, right? So you would think about using a nonce or something like that. So for security, that would be best. On the other hand, you have to keep track of this because at the time of verifying the pack, you need this, this modifier. So functionality, and you can't store this modifier anywhere, because if you have a way of securely storing that, say from the attacker, then you might as well store the return address there. So this is why you have to sort of find a balance. You have to find a modifier that's easier to keep track of without requiring additional hardware protection or anything like that, but try to make it as unique as possible. So in this Qualcomm return address protection, they decided to use the stack pointer as the modifier, which means that even if the same function is called from multiple places, the point authentication for the return address, the return address would be different depending on where the stack pointer is currently. And that's a trade-off. But you can imagine that if that is the case, then replay attacks are possible, because even though the attacker can't compute the message authentication for an arbitrary pointer, they can harvest pointers that they had seen before. And as long as the modifier is the same in another context, they'll be able to replace the authenticated pointer in the new context with the old one that they harvested. So if the stack pointer is used as the modifier, then the attacker can do replay attacks in any situation where the stack pointer is the same for the subsequent function call. So I hope this sort of gave you a taste of the challenges in using point authentication and sort of deciding how to build a protection scheme. And I'll refer to a couple of papers where we sort of, in the first paper that was in Usenix Security 19, we looked at A, how we can reduce the scope for these replay attacks, and B, how we can go beyond just return addresses, how to protect function pointers in general, but also data pointers. In the second paper, which was presented just a couple of months ago in Usenix Security 21, we asked this question, like, what is the optimal level of protection we can get? So I remember I said that ideally you want unique modifiers. So in the case of return addresses, we can ask, what is the unique modifier that you can get for any function return? And intuitively, it's the entire call stack. If you can somehow capture the entire call stack and use that as the modifier, then you know that it cannot be subject to replay attack with any other invocation, either of the same function or some other function. But what's taking a step back, what's interesting is we have this menu of different primitives that are being rolled out by manufacturers. You can ask, can we use it for different things beyond what was intended, like we did in these two papers? But you can also ask, how do these things compare? Control flow enforcement technology from ARM and point out from Intel and point authentication from ARM. They can both be used for return address protection. How do they compare? Is one better than the other? Is one more general than the other? This is an open, interesting open direction as well. And finally, of course, this all of this is kind of an arms race. So like Hans mentioned, ultimately, if you want to have confidence about the kind of protection you can get, you would need some way to formalize and analyze both the attacks and defenses. And the formal methods community had made like significant progress in analyzing protocols. And something like that would be also needed in analyzing runtime security mechanisms like these ones. So this is what I wanted to tell you, like give you a flavor of the kind of hardware assisted mechanisms that are coming up that can be effectively and cheaply used for runtime protection. And hopefully some of you are excited about these open research questions that one can follow. So now I will hand over to Long to conclude.
Okay, thanks, Professor Asokan. Okay, Salman, can you give me the control? Okay, sounds good.
Yeah.
Yeah. All right, so let me quickly wrap up the tutorial today. So in this tutorial, we discussed different advanced attacks and defenses. We show the breakdown of advanced attacks can give us a useful insight for system security assurance. We discussed the different types of data-oriented attacks and defenses. We also show a demo of the data-oriented attack. So Salman also show a demo of the various quantification methodology for security measurement. So as to the defense, we are especially interested in the hardware-assisted defenses. We believe, hardware-assisted defenses can be a very promising, direction against the runtime attacks. For the DOP attack, still there are, many challenges to fully automate the construction of the DOP attacks. How to construct the DOP attacks with minimum footprint, with minimum side effects is an open problem. We also think that moving target defense, like different randomization, can play an important role to improve the security of the system. I think that's for today's tutorial. I would like to thank everyone. Thanks for attending today's tutorial. Thanks.
All right. And we still have a few minutes left, and if you're not too Zoom fatigued after staying here for so long, feel free to ask question. And I have a quick question for Hans. So Hans, I think you already said towards the end that some of the DOP has sort of like JIT flavor. I know that the way that we set it up is sort of static, but then because some of the indirect calling relation or reference relations that you don't, there's this there's this concept of once you figured one leaked pointer, you may be able to discover more pointer locations. And so that in terms of fine-grained ASLR may not be very effective in terms of the DOP. And so could you maybe share more thoughts on this, in particular, sort of like just-in-time data-oriented programming with fine-grained ASLR relationship?
Also, just to remind Hans, he also has a question in the Slack. So after answering Dr. Yar's question, if you can answer that as well.
Yeah. Can't for some reason refresh the Slack, but yes, I will look into that. I haven't seen any attacks like that for DOP, but I don't see why the same principle wouldn't work there. I mean, I'm not sure if this answers your question, but
yeah, that confirmed my understanding. Yes. Well, if Hans, if you couldn't see the question, maybe someone can read it out.
So the question is, for DOP attacks, have you considered a process such as SafeCode? SafeCode ensures that pointers point to object in the correct point to set and is more efficient than Microsoft's DFI. So it's like SafeCode that computes the point to set for pointers and check whether any pointer is from that particular points to set.
Yeah, I think it sounds like a reasonable strategy, but I'm not familiar myself with that approach. But I think it sounds like a good idea.
Yeah, I think it's about the code pointer integrity checking. Yeah. So Professor Asokan also talked about the pointer authentication. Yeah, the approach probably is quite similar to that one. But nowadays we can use a hardware assisted feature to implement those defenses, which can be very efficient. Yeah.
Yeah. Also, just to add, like I'm also not familiar with SafeCode, whether it's only considered the code pointer or it's considered both code and data pointer. If it's considered only code pointer, then that is not enough, because also the data pointer, it's like it has the computation of the points to set up data pointer is pretty difficult job. So yeah.
And before we end, I just want to add that sometimes you see these layers of defenses, which is still very necessary because of the defense in depth strategy. We do want to have some redundancies in the defenses so that if one fails, the other can kick in. And so if time, certainly if especially critical assets that you want to have certain overlapping in the defense capabilities, and therefore understanding all these relative capabilities and security guarantees is very important. That's hopefully this tutorial will help you understand a little bit better. I for some reason don't see any questions on Slack. I don't know.
So there is a thread. The question is under a thread.
Yeah.
Oh, okay, gotcha. All right then. Any other thoughts? Well, if not, then I think our time is up. I'd like to thank everybody, our speakers, and feel free to follow along via email or on Slack. I think we're this is good. We'll remember to attend the next tutorial sessions and also the next two conference talks. All right then. Bye everyone.
Thank you.
Thanks, everyone. Thanks.
Bye.
Bye.
Mm.